Okay, so I think we are online. So let us start with the lecture. So first let me share the screen and then we will start. So okay, the screen is being shared and the pen mode is on, so we can start. So today we will be starting our new topic, and that new topic is strain. So until this point, we concentrated on stress and traction. So traction or stress is a function of traction, you can say, but that part is now behind us. And from today, we will be talking about strain. Now, if you go by the definition of strain that all of us know, I mean, even before entering engineering, there is something about strain that we studied. And by that definition, what is strain? So strain is basically change in length by the actual length. So if I talk about normal strain, so strain associated with the normal stress component is known as uh, the normal strain, and we define it as elongation per unit length. So that is how we define normal strain in a classical manner. But you will soon see that definitions will change, or at least the formulas will change. The well-known formulas that you already know, for example, del L by L, will no longer be applicable. But before we go there, uh, let us take one small example to explain the idea of strain that you already know. So suppose we have a fixed bar, right? So there is a fixed bar, and let us say this length of this bar is capital L, you can say it, and then there is a load, an axial load that is acting on the body, so we can call it to be F, and under the action of this load, what happens is the bar elongates. So let us say this is the elongate portion, okay? So this deformed or elongated bar length is given by small l, and for this bar the strain we define it by epsilon. So strain is nothing but final length minus initial length by initial length. There is another way of writing it, and that is L by L minus 1. And this L by L is known as the stretch. So this is known as stretch. So how much the bar is getting stretched, as we say, so this is known as stretch. Now there is a unique thing about this bar or about this strain. So for example, let us say, so let me again change color. Uh, Let us say there is a point A here and there is a point B here. So what will be the value of the strain at point A? The value of strain at point A is L by L minus 1. So this is epsilon A, and then the value of the strain at point B, which is epsilon B, will also be L by L minus 1, which means uh, for this horizontal bar, the value of strain does not change from one point to another. The value of strain does not change from one point to another. And since the value of strain is not changing from one point to another, we can call it to be the global strain. Right? Now let us take another example. And in this example, we again have a bar, and now that bar is being acted upon by its self weight or the acceleration due to gravity. So this is the self weight of the bar. Right. Now what happens in this case? So let us suppose in this case we have, similar to the previous case, we have 2 points again. One point is A, or you can call it A prime, and then there is another point which is B prime. But now since it is being acted upon by its self weight, what you can see if you want to compute is that epsilon A prime is not equal to epsilon B prime, which means the value or the magnitude of strain changes from point to point. So this means the strain changes from point to point, right? This means that the strain changes from one point to the other. And which means, what does it mean? It means in this case, therefore, for this case, global strain is not equal to local strain. So basically the point that I'm trying to make is that in a general setting, the value of strain will change from one point to the other. So we conclude that strain changes from one point to the other. The value of strain changes. So that is the point that I am trying to make here. And that is basically the take home message from this slide, that generally speaking, strain varies from point to point. That is the take home message from this slide. But now whatever we discussed were very basic, but also it was for a particular bar, or I mean this is a bar, so this was for a bar structure. But in 3D, a structure can be of arbitrary shape. So for example, you see a shape here, arbitrary shape, and then there is some boundary condition, and then it is being acted upon by some arbitrary force in some arbitrary direction. So clearly you can see here. So now the question is, how do we define strain for such a arbitrary body? So suppose we have a body such as this. say arbitrary body. So this is the arbitrary body, as you can see here, and then it is being acted upon by loads in arbitrary direction. There is no one direction because this is a 3D thing, anything can happen. So now, how are you going to define strain for this 3D body? That is the question. How are you going to define strain, or to be more precise, I should say longitudinal strain, because there are other types of strain as well. So longitudinal strain for a 3D body. So that is the question. So now you may think of let us say you may think of the basic definition. And what is the basic definition? Change in length by actual length. So you may tell me that I am going to compute the length, change in length, divide it by the actual length, and that is how I'm going to define strain at a point in this 3D body. But then my follow-up question will be, which length are you talking about? So are you talking about this length? Or you are talking about, let us say, this length? Or are you talking about this length? So there are infinite number of lengths. So which length are you talking about? So the follow-up question is, which length should we consider? So the question is, if we want to define strain in a 3D body as change in length by actual length, then what is this actual length? It is the length in which direction? There are infinite number of directions. So this brings us to an important point. And the point is, we need to define a line element for defining longitudinal strain in a 3D body. So we need to define a line element for defining longitudinal strain in a 3D body. So which means if we have epsilon, that epsilon is function of the spatial coordinate x, because strain varies from one point to another point, and it is also function of a line element n. Now if you recall in traction, what do we have? We have t as a function of x and n, but there is a difference between this n and this n. So let me write it down. So in traction, n represents plane normal. So you can also say that n represents a plane, or the normal to the plane, right? In strain, or in this case longitudinal strain, n represents direction of a line element. So there is no plane at this moment. There is only line element. And if you change the direction of the line element, the strain is going to change. So now with this in mind, that we need, for defining strain at a point, we need the coordinate x, capital X, and we need the direction of a line element, and it is along that line element that we are going to compute the strain. If I change the direction of the line element, the value of strain will change. So with that in mind, now let us see what will happen. So let us take a body such as this, obviously again an arbitrary body, and then say this is my boundary condition, and then under the action of some load which I am not showing here, this undergo deformation. So deformed. See, once it gets deformed, the shape is going to change obviously, right? So let us say it has changed, and this is now my deformed shape, right? Now, what did we just talk about? That for defining strain, we need the line elements and the coordinate. So let us say this is my coordinate. So this is my x. And then let us say this is my line element. So this is going to be d capital X, right? Now once it gets deformed, this point x is now shifted here. And that point I will call it small x. And this deform, this dx, which was a line, after deformation, that will in most of the cases not remain a line. So let us say this is my new, this is the line dx. So this is now dx. So what is the point here? The point here is let us say a line element before deformation will not remain a line in a general setting. That line will probably become a curve. But now, if we consider, or if we impose a limiting condition, and the limiting condition is dx is very small, so dx tends to 0. If that is the limiting condition, then the deformed curve can be viewed as a line because this is very small. So if we impose a limit, and what is the limit? Dx tends to 0, that is the length of the line element is very small. Length of the line element is very small. So if we do that, if we impose this limit, then we can say that the line element before deformation will remain a line, after deformation. So that is one of the consideration here, that the line element we are considering, we are going to consider it to be very small. Now there is one more thing that you need to remember, that we are talking about longitudinal strain. This is what we are talking about today. But there are other types of strain that exist in a body, and one such strain is volumetric strain. So this is something we'll talk about at the end, say for example, third lecture on strain. And then there is shear strain, and this shear strain we will be talking about just before talking about volumetric strain. So we'll start with longitudinal strain, then we'll talk about shear strain, and at the end we will talk about volumetric strain. But in any case, the take-home message from this slide is that for 3D case, longitudinal strain at a point in a body is defined based on line elements. So stresses were defined based on planes and plane normal. Strains are defined based on line element. So that is the point here. Now when I drew that diagram where there was an undeformed shape and a deformed shape, we could have defined strain, and that would have been change in length by actual length in the n direction. But then there is something known as strain displacement relation. So a body that is in the original configuration undergoes a change in its shape, and it is under the action of strain, and under the action of the strain and external force, the body undergoes displacement. And the question we are asking is, can we express strain in terms of displacement? So the question we are asking is, can we represent strain in terms of displacement, right? So that is the question in here. So there is a big derivation here which I'm going to do, but obviously since the derivation is quite big, it will not come in a single slide. So I will do the derivation, then refer to the slide, and again do the derivation, right? So let us start. So the first step is we are going to consider a coordinate system. Okay. So let us say this is my coordinate system. Then let us say this is my body, and then on this body there is a point x. What is the value? X vector is represented by this dotted line, right? Now let me change the color of the pen. Now under the action of some external force or external displacement, this body undergoes displacement and deformation. This is a deformable body, so it will undergo displacement as well as deformation. And then what will it look like? Let us say this is my deformed shape, right? So this is my deformed shape. Now there is this point x, capital X was there. Now that point here in the deformed body is small x. Okay. So what was capital X previously has become small x. Now we are talking about longitudinal strain. So for defining longitudinal strain, we will need to define a line element, and we will indeed define a line element. But before we do that, let us do something more. Now, what you are seeing here, so let me change the color once again. So what you are seeing here is the reference frame. So when we are going to consider displacement everything is to be computed with respect to the reference frame. So at this point, this is a reference frame. So at reference frame, we have t equal to 0, right? And then this is the, let us say, frame at t equal to t. So that is the first thing. So this is undergoing some deformation. Okay, this is undergoing some deformation. Now, one thing that I will need to do is this small x, the deformation, is going to be a function of the capital X. So what I can do is I can write small x is equal to some function of capital X. So what does it mean? This means deformation or displacement at this point will be different from displacement at this point. So this point, let us say this is y, capital Y, this will become small y. So obviously you can see that capital Y is not going to become small x. So whatever deformation is going to change, that is a function of the initial configuration, right? Now remember that this function f is a vector valued function. So what does it mean that f is a vector valued function? So what is x? X is, let me make it blue for more clarity. So what is small x? Small x is actually nothing but this vector, right? So if you write small x in terms of its component, it will be x1, x2, x3. And then what do we have here is capital F, x1, x2, x3. This is f1, f2, x1, x2, x3, and then f3, x1, x2, x3. So clearly you can see that there are three outputs from this function f, and that is why we call it a vector valued function. So now this was x, capital X, and this is small x. Now what is the deformation or displacement in this case? Okay, let me change the color again. So the displacement is this one, right? So this one is your displacement u. And since displacement x, capital X, small x, all of these are vector, what we can write? We can write that u is u is a function of obviously x and capital X, but u is basically small x minus capital X. Remember that all the three quantities are vector, so it is a vector subtraction. It is not a usual subtraction that you do. So, and then what we can write, if u is x minus capital X, we can write fx x as this one. So what do we have? We have f capital X minus x. So this is for now your relation between u, fx and x. So this is my relation. U is equal to fx minus x, right? So this is my relation. So now remember this one, as I will be referring to it at a later stage. So let us see. So this is what we talk about, f, x and t. So this t I did not include because we are not considering dynamic system in this case, but obviously x is also a function of small t. So at t equal to t, if this is the configuration, at t equal to some other value, this may be the configuration. So obviously this x also depends on time t, right? So yes, that is also there. And then this is basically the deformation. I mean, this is the this x to capital X, and then we have, I mean, this one, right? This one we talked about, that u is basically fx, because this is nothing but small x uh, minus capital X. So this distance you are seeing now is basically u. So now let us go back, and then what we will do is we will proceed further. So quickly let me draw the coordinate axis. Uh, this is initial configuration, the reference frame. This is the deformed shape. There is this capital X. There is this small x. Now x becomes, so this is a new point. So we need to take a line element. We discussed it already. So this is now my line element, and this is x plus dx, right? And then what do we have here? What we have here is small x, and small x will become, uh, so this is now my new point. So this is, so basically when I'm saying x plus dx, this is this point, okay, and this point. So this point is now my uh, small x plus dx, okay. Now what is the value of this point that I have not shown? This point is y, you can say, and this point is small y, right? So that is exactly what we do here. So you see y, we make it to be x plus capital del x, and small x we made to be small x plus delta x. And now what we want to do is we want to find out the length of this delta x, because this is my uh, change in length, right? So this is what I want to find out, small del x. So how can we find out small del x? So let me see. So this is your initial configuration. This is capital X. This is your line element, and this is x plus dx, which is basically capital Y. Then we have this one. So we have small x. Small x becomes small y, which is nothing but x plus dx. Now, what we want to know is the change in the length. Now, there is a limiting condition, and that limiting condition is dx tends to 0. And with this limiting condition, this curve you are seeing here will become very close to a straight line. So now let us see what we can do. So this is x plus dx, this is small x plus dx, and I want to find out this dx. So what is this dx? This dx is y minus x, right? This dx is y minus x. Now what is y? Y, if you remember the relation, we have x is equal to that vector valued function of capital X. So obviously from that thing, f is equal to vector valued function of capital Y. So this is f y, and this is minus f x, right? And what is Fy now? We know that y is x plus dx. So Fy is f x plus dx minus f x. So this is what your length is, and since this is a length, we can write it like this one, right? We are trying to finding out the length dx. So that is basically the magnitude we are talking about. So this is what we have: f x plus dx minus fx. Do remember that this dx has three components: dx1, dx2, dx3. So this is a vector valued function, which is okay. But even this dx, the capital Dx is a vector, so it has three components. So that is something you should remember. Now what we are going to do is, okay, let me go to the next slide and then come here. So what do we have? Dx is equal to f x plus dx minus fx. Now what we are going to do is we are going to use the Taylor series expansion. So using Taylor's series expansion on the first term. So if you do that, what do you get if you use Taylor series expansion? So this dx is there. So first it is f of x plus del f by del x1, the first component of dx, times, so it is Taylor series expansion times h. H is basically dx1 plus del f by del x2 dx2 plus del f by del x3 dx3. Now in a one-dimensional Taylor series expansion, you only get one first order term, but in a vector valued function or in a multi-dimensional Taylor series, you get multiple first order terms. In this case, there are three components, like x has x1, x2, and x3, and that is why you are getting three first order terms. And then there are the higher order terms which I am going to include. I'm going to omit. Minus there is fx. Now remember, we are working with the assumption that dx is very small. We are working with the assumption that dx much less than 1, which means all the higher order terms where there will be dx square, dx cube, and all those things can be ignored. Therefore, higher order terms can be ignored, right? The higher order terms can be ignored. So if we ignore the higher order term, and there is another thing we can do, so there is fx here and minus fx here, so we can cancel it out. So what is the final thing we are getting? Dx is equal to del f by del x1 dx1 plus del f by del x2 dx2 plus del f by del x3 dx3, right? Now let me clear up some space because I want to do one last thing and last two things actually with this. So let me erase some of this zone or some of this equation actually so that I can use or reuse those places. So yeah, so what I'm going to do is actually very simple. I am going to represent this equation, the equation of dx, uh, by using I'm going to represent the equation of dx uh, by using a matrix notation. Okay. So what do I have here? Let us see. Dx, right? There is one mistake I was making. This will not be there. This is not dx. We are called because if is still a vector function, we are getting three values of dx. Okay, so that is something wrong. So can we write it in matrix form? Yes, we can. So this will become df by dx1, not d actually, del, right? Del f by del x2, del f by del x3. And then we have dx1, dx2, dx3. Now remember that f is a vector valued function. Vector valued. So if I write, if I write the vector valued function in terms of its components, it will look like del f1, del x1, then we have del f2, del x2, del f3. Okay, let me clear this up. This is creating problem, so I will erase this. So yeah, this portion I will clear it up. So obviously the last term will be del f3 by dx3, right? Del f3 by del x3. Okay, this is wrong. Del x1, right? Then we have del f1 by del x2, del f2 by del x2, del f3 by del x2. And lastly, we have del f1 by del x3, del f2 by del x3, del f3 by del x3. So this is the complete matrix that you are seeing here. And then we have the dx1, dx2, dx3, right? So what we have at the end. Uh, let us write it down and then we will move to the next slide. So let us see what do we have. We have something very interesting here. What we have here is dx, not capital X, d small x is equal to f d capital X. So this is, I'm calling it to be my F matrix. This is also known as the, I'm not sure the name, but I think it is also known as the deformation gradient, either deformation gradient or displacement gradient. I think it is deformation gradient, but I will check and let you know. Okay. So, but in any case, we have a relation that dx is equal to f times dx. So if you know small dx the length, if you multiply it by f, you can get your length small dx, which is the length in the deformed configuration, right? So let us see. So these are all things that we have done, right? And then this is the matrix F that I was talking about. This is the matrix F that we're talking about. Yeah, this is something that I did not talk about. So let me talk about this one. So if we are talking about capital F, which is basically gradient of small f. So now since f is a vector valued function, you can write it in a vector notation such as this, which is actually very simple. What I'm doing here is, this is my E1 direction, this is my E2 direction, and this is my E3 direction. So like we did with the traction, you remember what we are doing? So if you remember, we did this thing with traction actually. So resultant traction was summation I equal to 1 to 3 T, so it was N, right? EI dot N. So something like this we did while computing traction. And then what we did was, if you remember, we wrote it as summation I equal to 3. So it was Ti. So it was Ti cross N, and then there was Ti cross EI dot N, and this Ti cross EI summation was actually giving you sigma, right? Sigma is basically nothing but summation I equal to 1 to 3 Ti cross EI. So, and then when you wrote it, you found out that the first column of sigma is T1 cross E1. So first column was T1 cross E1. Second column was T2 cross E2. Not exactly second column, but this is what we are doing. And this was T3 cross E3. So similar thing we are doing here. So the first one is del F by del X1. So del F by del X1 cross E1 plus del F by del X2 cross E2 plus del F by del X3 cross E3. So this is vector representation. This is vector slash, you can say, tensor representation, and this is actually quite similar uh, to how we represent stress in terms of traction. If you remember that part, it is quite similar. But in any case, this is our final thing. This is what we get. That is del x is equal to F times capital del X, right? So now this is what we have. And we are going to work with this to find out something interesting. So let me go here. So what do we have? We have del X is equal to F del X. Now you remember the definition of strain. What was the definition of strain? Or at least longitudinal strain? L minus L by L. Then I wrote it as L by L minus 1. And this is my stretch. So that is what I want to compute, stretch or stretch square, you can say. So suppose I want to find out my final length. So final length is L square, which is basically, final length square is L square actually, del X dot del X. And then what we can do is, we can write it as if delta X dot if delta X, right? And then if you take this capital L square, that becomes capital X dot capital X, right? And what is capital X dot capital X? Capital X dot capital X, the del X is nothing but magnitude of del X square, which means I can write it as magnitude of del X times magnitude of del X. So now what I'm going to do is stretch. So let us say lambda is my stretch. So lambda square is L square by L square, right? And then what is L square? L square is F delta X dot F delta X divided by this term. Okay, there is one problem here. This is capital X, right? So this is capital X. So now what do we have here? Delta X delta X. Okay. And now finally, what I'm going to do is I'm going to take one delta X couple with it, this another delta X here. So what do we have here? F. And then we have delta X by magnitude of delta X. And then you dot it with F delta X by magnitude of delta X. Now let us do one thing. So let us go back to vector. Suppose I have a vector A, right? And then that vector is represented by A1 I cap plus A2 j cap plus A3 k cap. So that is my vector A. Now what happens if I divide A by magnitude of A? What do I get? What I get is the direction cosine. Because this becomes a unit vector, and when it is a unit vector, all I get is the direction cosine. Cosines, or basically the unit vector, or yeah, the unit vector, right? So, and what is the unit vector? We took an initial direction, remember? So when you draw this, you started with the initial direction. This was x, this was dx, and this point y was x plus dx. So let us say this direction is n. So what we have here is m, f times the unit normal vector n dot f times the unit normal vector n. So that is what we have here. You see, that is what we derived, because del x by magnitude of del x gives you the unit normal vector. So what do we have? Let us see. We have a relation between lambda square, which is stretch square, and f. And what is f? F is deformation gradient, right? Now, our initial goal, what was the initial goal? The initial goal as written here is to find out the relation between strain and displacement, and our displacement is u. So somehow we have to represent f as a function of u, right? So let us see how we can do that. How we can represent f, the capital F, as a function of u. So you remember the coordinate system that we started this derivation with. So this was the initial one. This is x, and then some final one, and this is small x. So this is actually this capital X vector. This is the small x vector, and this is your u. So yes, so there is an angle here, right? So your u, if you remember, is f of small x. Sorry, is u is actually small x minus capital X, and your small x is actually a function of f of capital X minus x. So with that, if I take gradient of u, so gradient of u, it will become gradient of f, which is capital F, right? So this is capital F. And x, with respect to x, we are taking gradient, so this will become an identity matrix. So with that, what do I have? You see, gradient of u is equal to f minus I, which means f is equal to I plus gradient of u, right? So this is what we have. So now let us see what we can do with this. So what was the relation we have? Lambda square, we derived lambda square as f n dot f n. Now what is this f? F is basically I plus delta u n dot I plus gradient of u n. So we have something like an dot an. So we can write it as, using vector again, as A transpose A n dot n. So that is what I'm going to do. So this will become I plus gradient of u transpose times I plus gradient of u n dot n. So this is how we can represent it. And this is lambda square. So we do that thing here also. And lambda square is I plus gradient of u transpose times I u n dot n. I mean, so I have kept it in the middle, but you can also move it to the side now. Okay. And then what we can do is we can write it in this form, where basically we can basically write it in this form actually. So if you look into this, what do we have here? Let us see. So let me go to the white screen. So what do we have? We have delta, no, not delta x, lambda square is equal to I plus gradient of u transpose I plus gradient of u n dot n. Now I am going to do this multiplication, and that will give me I plus gradient of u plus gradient of u transpose plus gradient of u transpose gradient of u, right? Now u, we are going to assume that we have already assumed that dx is small. We also assume that the displacement and displacement gradients are small. So we are working in the small displacement zone right now. Actually, we are working in the small strain, small displacement zone, but for now we can say we are working with small displacement. We also assume that the displacement and the displacement gradient are small. And with this assumption, this term vanishes. This becomes 0. So what we have is lambda square is equal to I plus U plus U transpose N dot N. And this is basically my stretch square. Okay, this is my stretch square. Now, if I have to write it further, this I n dot n is unit vector, so that will become 1. And then what do we have? Gradient of u plus gradient of u transpose n dot n. Right? That is what we have. Now, this is, we are talking about lambda square. But for computing strain, it is lambda minus 1. So I need to compute lambda. So we take square root of both sides. So lambda is square root of 1 plus gradient of u plus gradient of u transpose n dot n. And if we use Taylor series, if we use binomial expansion, and similarly, if we ignore the higher order terms, we have 1 plus half gradient of u plus gradient of u transpose n dot n. So let me go again. So what we have is lambda is equal to 1 plus half gradient of u plus gradient of u transpose n dot n, right? Which means epsilon, which is lambda minus 1, is half gradient of u plus gradient of u transpose n dot n, and this is your final result. So let me write it down once again and then box it. So this is the strain displacement relation, and we are talking about, remember always that we are talking about longitudinal strain here. So this is the relation between longitudinal strain and displacement, right? So this is your strain displacement relation in a vectorized form. So if you look into here, this is your strain displacement relation, the same relation that we discussed earlier. Now, if we want to find out some special cases, so let us say we have this coordinate system, where this is E1 or X, this is E2 or Y, this is E3 or Z, then what do we have? Epsilon 1 if we want to compute. You can compute it from here. What will happen is, okay, let me go to a white screen. So I want to compute epsilon, right? First, let me write down the formula. So this is half gradient of u plus gradient of u transpose n dot n. And then we have this one. So this is E1. And E1, if you remember, is 1, 0, 0. So if I want to find out epsilon 1, 1, and let us do this thing. So what is gradient of u? Gradient of u is del u1 by del x1 del u2 by del x2 del u3 by del x3 del u1 by del x1 x2 del u2 by del x2 del u3 by del x3. So this will get to this point. Del u1 by del x3 del u2 by del x3 del u3 by del x3. So this is this part, right? And I have to add it by the transpose of this part. So what is the transpose of this part? Let me write it down. Transpose of this part is the diagonals will be same. And what we have here is del u3 by del x3. But the other things will change. So this will become now del u2 by del x. Okay, there is something wrong here. I can see. So del u2 by del x1, del u3 by del x1. Then this becomes del u1 by del x2. This becomes del u3 by del x2. This becomes del u1 by del x3. This becomes del u2 by del x3. So this is the transpose part, right? And if you do this, do the addition, you will get a symmetric matrix, and what you will get is okay. I'm trying to save space, but I cannot, so I have to write it here only. So this will become twice. This will become twice. This will become twice when I'm doing the addition. So this is no longer there. I am adding it up with this one. So this becomes twice, and this becomes del u2 by del x1. This is symmetric, so this will come here, and this becomes plus del u3 by del x1. Again, this is symmetric, so this should be identical to this one. And this one will become del u3 by del x2. And this is symmetric, so this will come here. And then if you take the half inside, this 2 will vanish and half will come here. But in any case, we have a symmetric matrix. And all we are interested in is this part, okay? So we have, if you look into it very carefully, del u1 del x1. Then we have some term here, symmetricity, so the other half will be automatically same. Some term here, and then del u3 del x3. But now there was n dot n, this part, which will become e1 dot e1, which is this one. And as you do e1 dot e1, what you will see is that only this term will be remaining. Everything else will become 0. I mean, only this is the only term that you will get, which means epsilon 1 is basically del u1 by del x or del x1. Similarly, if you do it for epsilon 2, you will get del u2 by del y, and for epsilon 3, del u3 by del z. So these are your well-known strain displacement relations. So these are the well-known strain displacement relations. Okay. So we'll stop here, and in the next lecture we will talk about strain displacement relation, obviously, but for shear strain. So the next lecture will be on shear strain. We will define shear strain, and then we'll try to find out the strain displacement relation for shear strain. Thank you, and we will meet again in our next lecture.